Hello everybody and welcome to our video on section 16C, stationary points. So just a little review. If we have a polynomial function, something like this, it has some points of interest. We have a local maximum here at -2 and 4 because it's a high point relative to the points nearby. It's not the highest point, but it's a bump compared to the points nearby it. Likewise, we have a local minimum here, which is a relative low point, okay, where y gets the lowest that it gets relative to the points around it. Okay. This function, we also have a global maximum here because it's the highest point that y gets, the highest y value that we get in the whole shape. And we have a global minimum here because it's the lowest that y gets in the whole shape. Now, the endpoints are not always the global minimums and maximums. They just happen to be in this picture. Now, we've also got a new kind of point that we care about, a new stationary point, and it's called a stationary inflection. So stationary inflection is a point, it usually happens in a cubic function or a part of a function that is bigger than a cubic function, where the function goes from increasing at a fast rate to a slower rate, and then it goes flat, and then it starts to increase again. So it's increasing on both sides, but it goes flat, perfectly flat in the middle. And what's special about these stationary points is that the slope of the tangent at these local minimums and maximums and at stationary inflection points is always horizontal, and therefore has a slope value of 0. Okay, so a stationary point of a function is any point where the derivative is equal to 0. If the slope of the tangent is equal to 0 because it's horizontal, then the derivative is also equal to 0. It could be a local max, a local min, or a stationary inflection. So what happens to the sign diagram? How could we tell what the shape of the function is without looking at the graph? Well, we can look at the sign diagram. In this case, my function is increasing, so it has a positive derivative here until it gets to this local maximum, and then it's decreasing. Okay? Then it reaches another stationary point and it starts to increase again, okay, and then it starts to increase after that. So if we have a local maximum, our sign diagram will be positive before and negative after, meaning the derivative would be positive before that point and negative after, indicating increasing, then decreasing, which suggests a maximum. If we have a local minimum, our derivative would be negative approaching that point, positive after that point, suggesting that the function is decreasing and then increasing, which suggests a local minimum. And if we see two signs that match, either increasing, positive, positive, indicating increase, increase, or negative, negative, indicating decreasing, decreasing, then we have a stationary inflection point. So in conclusion, the changes in the first derivative over a turning point can tell us about the nature of the turning point, if it's a local max, a local min, or a stationary inflection point. And we call this the first derivative test. Now, the first derivative test says if we have a critical number, which is also what we've been calling a turning point or a point of interest for a function f, if the derivative changes signs from negative to positive, we have a local minimum. If the derivative changes signs from positive to negative, we have a local max. And if it does not change its sign at c, then it's neither a local min or a local max. It is a stationary inflection point. In our next video, we'll look at an example of this. Thank you.